Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. In Part A of Module 10, we introduced two cryptosystems. One is the conventional cryptosystem. The other one is the public key cryptosystem. Now, the conventional cryptosystem is also called symmetrical system. Now, in symmetrical system, both the user and the sender use the same key, and most likely they use the same algorithm for encryption and decryption. Now, in public key cryptosystem, now each user gonna create two keys. It's called a pair of keys, and one is the public key, the other one is a private key. Now, these two keys are typically not the same, but they are related. Now, so one of the key is used for encryption, the other key is used for decryption, and depend on the scenario, we can either use the public key for encryption and use the private key for decryption, or vice versa. Now, in Part B, we're going to talk about the RSA algorithm, which is a very, very important public key encryption and decryption algorithm. RSA stands for Rivest, Shamir, and Edelman. These are three professionals working in MIT. Okay, so the RSA was developed in 1977 at MIT by Ron Rivest, Adi Shamir, and Len Edelman. So RSA is widely used general purpose approach to public key encryption. Okay, now RSA is actually a encryption and decryption algorithm in which the plain text and the cipher text are integers. Okay, now the typical size for integer is 1024 bits. Now, it was smaller, but since the computer becomes faster and becomes more powerful, so they increase the size for the number n. So now the typical size for the number is 1024 bits for binary number, or equivalently, it's about like a 309 decimal digits. Now think about this number. It's a huge number. Now think about the decimal digitals, which contains more than 300 digits. Now it's likely that the size of the number going to increase as the computer becomes more and more powerful. RSA makes use of an expression with exponentials. Now, we can actually perform the modular operation on these expressions. Okay, plain text is encrypted in blocks, with each block having binary value less than some number n. Now, this number n is very important. Remember, in the previous slide, we just talked about, the RSA should actually choose the value n, which is about 1024 bits for the binary number, or which is equivalent to like a 309 decimal digit. Okay, now this n is very important. And then with the n, once we select n, then for every number m, which is less than n, we can encrypt the n using the RSA. Now here, the encryption and decryptions are very important and also very simple. Okay, so here's how we're going to encrypt the number. So we're going to actually perform the M, which is supposed to be the plain text, to the power E, okay, and modulo N. So then hopefully this is going to be the ciphertext. Now, M is a plain text. N is the number we select, a huge number, right? And what is E? E is supposed to be part of a key. Now, this could be part of the public key or part of the private key. So it must be part of key. Remember, in public encryption algorithm like RSA, we should have two keys. One is public key, right? The other one is private key. Now, E should be part of the public key or part of the private key, depend on the scenario. Now, that's for encryption. Now, the decryption is very similar and also very simple. So suppose we have a ciphertext. Now, the decryption is going to perform the similar operation. We're going to perform C to the D modulo N, sorry. And what is D? D should be part of the other key. Okay, if E is part of the key, with whatever the key it is, it could be public key, and then D should be part of the private key. Okay, so E and D are somehow related. So hopefully we can actually, the result should be the plain text. So we should be able to restore the plain text. Okay, so that's the encryption, decryption. So the encryption and decryptions are very simple. And it should be relatively easy to calculate. It doesn't matter how big the N is, how big the E is. Okay, so they should be relatively easy to perform, right? Because remember the properties for the modular operation. So we can perform this, right? So if you calculate this, and then you can calculate M to the E, and then we can do something like M squared to the E half E N, and then we can actually put the M squared mod E or mod N, then E divided by 2 mod N, right? So we can actually, hopefully, we can reduce the number of power. So we can keep doing this, so we can easily calculate this. And we can also easily calculate this, okay, even though M and C are very big. Now, in order to perform this, we need to actually make sure the E and the D should be somehow satisfy certain relationship. So we can discuss these relationship. So number one first, the first one is both sender and the receiver must know the value of N, because in both the encryption and decryption requires the modular N operation. So both sides need to know the number N, okay? And also, somehow, the sender needs to know the value E, and the receiver needs to know the value D, okay? E could be part of the public key, right? Or could be part of the private key. Then the D is the other one. If E is a part of public key, the D is part of the private key, okay? So now what is the public key? Later on, we're going to find out. The public key is actually the combination of E and N. The private key is a combination of D and N. So, or vice versa. You can make the E and N the private key, this one as a public key. Okay. From this perspective, E and N and D and N should be somehow symmetrical or equal. So remember, in the previous slide, we said that the encryption should be very simple. So once we have a plain text M, and we know the D, or know the E, sorry. So we perform M to the E modular N, and this makes the ciphertext, right? That's the plain text, and that's a ciphertext. We also say that the decryption should be very similar. We should perform M to the, I'm sorry, not M, C to the D mod N, and we should, select the value E and the D such that the C to the D mod N is M. So we can restore the plain text. Now, in order to make these two true statements, we have to make sure that certain conditions are true. So we have to make sure that the M to the ED mod N equals M. Why is this? Because if C is, sorry, again, is M, if we hope that the C to the D mod N is the plain text, then we need to substitute the first statement, right? So replace C with the right side. So we can basically make C to the M to the E mod N, replace C with this, to the D mod N, right? Now, based on the property of modular operation, if we have mod M to the E mod N to the D mod N, then we can actually remove this. This is the same as M to the E D mod N. So this is the same, right? That's basically based on the property of the modular operation. Now, if you forgot this, just go back to the previous module, module 9, to find out, right? Remember, this is actually generally true for any number. So that means M to the E times D, M to the E D, then this is the same as M to the E times D, N. So that means M should be the same as this. So M to the ED mod N equals M for all M. Okay. Now, we will find out that it's relatively easy to calculate M to the E mod N and the C to the D mod N for all value M. However, we should choose the N and the E and the D so that it's infeasible to determine D given E and N. Because remember, we make the public key as the E and the N, right? So that means this value N and also E is known to everyone because we're going to make these E and N public. So this is part of the public key, right? So now if we know E and then we know N, now we should actually choose the E and the D such that even though people know E and N, they still cannot determine what is the value D. Okay. So that's an important part of the RSA. So the encryption and the decryption for the RSA are very simple, relatively easy. So now let's focus on the other side. The important part of the RSA is how can we find the number N, how can we find the number E, and how can we find the number D. Okay, so finding N, E, and D becomes the most important part for RSA. So that's the reason why finding the number N and also finding the public key and the private key are the most important part of the RSA. That's the key for the success. Okay, so now let's talk about how to generate these public key and private key pair. Okay, so in order to do this, here's the process of generating the public key and the private key. The step number 1, we need to select 2 large prime number at random. Let's say we select a 2 large prime number. Okay, how large is this? It should be very, very large. Okay, and then we multiply P and Q. Once we find 2 prime numbers, we multiply these 2 prime numbers, and we got the number n. Okay, now that's the number that we want to determine first. Okay, so now if we want to make the n very big, so big that it's close to like 1024 bits or 309 decimal digits. So that's the size of the number. So that number should be like this size. Now, if the n should be about like 1024 bits long, then what's the size for P and Q? What's the size for P and Q? P and Q should be very, very big. Okay. Now let's think about this. So let's say n is about 309 digits. That means n is about 10 to the 309 times something, right? So now n is a multiplication of P and Q. So let's say, assume that P and Q are about the same size. They should be different, but let's assume they are about the same size. Okay, so that means we can write n as 2 numbers, P and Q. And the multiplication should be 10 to the 309. That's about the size of this number. Okay, now what is a Q? P and Q. P should be at least about 10 to the 154, right? And the Q should be about 10 to the 154, or maybe we can make it one a little bit bigger, 10 to the 105. So that means P times Q becomes 10 to the 155 times 10 to the 154. That makes about 10 to the 309. So the value P should be in the neighborhood of 155 digits, and the Q should be about 154 decimal digits. That's still a huge number, right? So we're going to try to find 2 prime number, which is about 10 to the 155 and 10 to the 154. That should be the size of these two prime numbers. Now, what's so good about this? Now, we're going to find out, in math, once we actually find out 2 prime numbers, now we can easily multiply these 2 numbers and get the number n, right? That part should be relatively easy. Not that easy, but compared with the other way, it should be relatively easy. Now, even though I can multiply these two numbers, which is these are two huge numbers. So now multiplication is not that easy, but it's doable. Okay, so once you got P and Q, then we can multiply these two numbers and we got an N. Okay, now that operation should be relatively easy. I'm not saying it's very easy, but relatively easy. Now, what's so good about this? Because in the RSA, we're going to use the Euler's Tautian numbers, okay, or Euler's Tautian function. I'm sorry. So remember, the Euler's Tautian function for n, if we try to calculate the Euler's Tautian function of n, it's very, very difficult. It's impossible because we have to find out. Remember the definition for the phi of n, the Euler's Tautian number. It's defined as the number of integers smaller than n and relatively prime to n, right? So in order to do this, so we need to check each of the individual numbers, which is smaller than n, whether this number is relatively prime to n. So we need to check one by one until we check all the numbers which are smaller than n. Then we say, oh, how many numbers are relative to n? That's the Euler's Tautian function, right? However, if we know n is the multiplication of two prime numbers, things are very, very simple. Why? Because remember, so we know that the phi of n, if n is the multiplication of p and q, and both p and q are prime number, then we can actually, or relatively prime, then we can write this as phi of q times phi of q, or phi of p times phi of q. Okay. Now, what is phi of p? What is Euler's Tautian number for a prime number? Because p is a prime number, so every number smaller than p should be relatively prime to p, right? So that means all the numbers from 1, 2, 3, 4, all the way to p minus 1, these numbers are all relatively prime to p. So that means the Euler's Tautian number phi of p is p minus 1, and the phi of q is q minus 1. So the phi of n can be calculated easily by multiplying p minus 1 and the q minus 1. That's also important, okay? Remember this, okay? And then we're going to select at random the encryption key E. We're going to select the E, randomly select the E. So we're going to randomly just generate a number E, which is less than phi of n and greater than 1. And also we want to make sure the GCD, the greatest common divisor between E and phi of n, is 1. So that means E and phi of n are relatively prime. Now how can we select E? So we randomly select E, and then we check E and phi of n, which is this, right? Phi of n. So we check whether these two numbers are relatively prime. Now that process should be relatively simple, right? Because we can use the Euclidean algorithm, right? Using the Euclidean algorithm, we can easily calculate the greatest common divisor between E and the phi of n. Now, if the GCD of E and the phi of n is not 1, that means they are not relatively prime. That means we just get rid of this E and select another E. We select E, randomly select E, and check whether E and phi of n are relative prime. If it's not, then we abandon the E and select another E until we find E such that GCD of E is and phi of n is 1. So that means these two numbers are relatively prime. Okay, suppose we find E. So now we got our first key because we have E, we have N. Okay, so E and N make a very good key. Now the next step is to solve the following equation. We're going to find an integer d such that the E times d is 1 modulo phi of n. So in another word, we try to find a d such that E times d modulo phi of n is 1. So it's like we solve the function. We know E, we know phi of n. We try to find the d such that the E times d modulo phi of n equals 1. And this is relatively easy to do, even though we haven't mentioned that one yet. But there's an algorithm to calculate the d once we know E. Now that d is actually the inverse of E modulo phi of n, right? So E and D are inverse to each other. It's a multiplicative inverse to each other. Once we find the d, then we can define, the public key. Okay, so we could use I don't know why I use KUKR. It should be PUPR. So P of U is EN. P of R, PR is DN. So that's the private key. That's a public key. So that's public key. That's private key. Okay. So then we find N. Now we use capital N. We find N, and also we find E, and we find D. And E and D are multiplicative inverse to each other, modulo phi of n. So that means E and D modulo phi of n is 1. So that means E and D are multiplicative inverse modulo phi of n. So this is so important. Okay. So this is the way we can actually, for each user, to find a value n and find the value E and find the value D. So that makes the public key and a private key. Now let's see why this is working. So before we move forward, let's summarize the RSA algorithm. So the first part of the RSA algorithm is to find N and the E and the D. Okay, so in order to do this, we first select the 2 prime numbers. Okay, so these 2 prime numbers are not the same. So then we calculate the P times N, and we got N. So now we got an N, right? And then we calculate the Euler's totient function of N, which is phi of N, which is actually P minus 1 times Q minus 1. We know from the previous slide, right? And then we select integer E such that the GCD of phi of N and E is 1. And E is between 1 and phi of N. And then we calculate the D, which is the multiplicative inverse of E modulo phi of N. Or in another word, so E times D modulo phi of N is 1. And then we make the public key, which is E and N, private key, which is D and N. So the encryption is very simple. For every plain text, which is actually which is less than n, then we calculate the ciphertext by n to the e mod n. We got ciphertext, and decryption should be, c to the d modulo n, and then we restore back to n. And remember, e and d are related, right? Now let's analyze RSA further and show why RSA works. Now before we do this, we need to recall the Euler's theorem. The Euler's theorem says if a and n are relative prime, then a to the phi of n modulo n is 1. Please remember this. If you have forgot, then you need to actually just go back to module 9 and review these Euler's theorem. And also in RSA, we just mentioned how to create the keys, right? The pair of keys. And the first step is to generate two prime number p and q that are not the same, and then multiply p and q and generate n. So we try to calculate the phi of n, which is Euler's total number, a function of n. So which is actually p minus 1 times q minus 1. We can easily see this, right? Because phi of n is phi of p times q, because n is actually p times q. Because p and q are prime number, so we can calculate the phi of p times calculate phi of q. That's the same. Now p is a prime number, so the Euler's total function is p minus 1. And the q is also a prime number, so phi of q is q minus 1. So the next step is to select one of the key, e, right? One of the key, which is e first. So we select e, which is greater than 1 and less than phi of n, and make sure the e and the phi of n are relatively prime. Now, if e and phi n are not relatively prime, then abandon the e and select another e. So until we find e such that the GCD of e and the phi of n is 1. So once we find the e, then we try to find the d. So such that the e times d modulo phi of n is 1. So that means e and d are multiplicative inverse modulo phi of n. So in another word, so if we actually divide e, so e and d are divided by phi of n, we got remainder 1. So that means we can write e times d as phi of n times some number k plus the remainder 1. So in this case, k is the quotient. So that means when you divide e times d by phi of n, you got a quotient k and then the remainder 1. So you can write e times d as this. So we got this one. So now we're ready to prove that the RSA actually works. Now first, let me actually erase these things. So I'm going to free up the space so I can just do the analysis. Let's just erase everything here. Okay. So now let's take a look at the RSA and show why RSA actually works. So for any plain text m, which is less than n, so we're gonna do the operation m to the e modulo n, right? So we calculate the ciphertext that way. So m to the e modulo n is a ciphertext c. And also we want to show that once you got the ciphertext c and the c to the d mod n, if we do this, we will actually restore back to the plain text. And we want to show this, right? So let's see. So let's see, C to the D mod n. Now we replace the C with this expression because that's how we got the C to the D mod n, right? So then we got m to the e mod n to the d mod n. So then we can remove one of the modular by the property of the modular operation. So we can basically write it as m to the e to the d mod n, or n to the ed mod n. Now we replace the ed using this statement, this expression. So ed can be written as 1 plus k times phi of n mod n. Okay, now let me write one more expression so we can better understand this. This can be written as m times m to the k phi of n, right? Mod n. Okay, so we can write this one as the multiplication. We separate these two items. Now the first item is m. The second one is, so we can actually, by actually modular operation, we can put the actually first item m. So let's say m mod n, right? Times the second item, m k times k to the n, m to the k times phi of n mod n. Now the whole thing under mod n. So we can separate these by calculate the modular operation for each first, and then do the modular operation. Now the first one is nothing because m is less than n. So the mod n, m mod n is actually the same as m, right? Now the second one, what is the second one? Now we will find out that m to the k times phi of m, this can be written as m to the phi n to the k mod n, right? This one can be written as this, and this can be written by the modular operation m to the phi of n mod n to the k mod n. Now what is this? This looks familiar, right? M to the phi of n mod n. So looks like the Euler's theorem can apply to it. So this is going to give you 1. So 1 to the k mod n. 1 to the k is 1. So this is 1 mod n. That's 1. So this second term is 1. Mod n. So m times 1, that's 1m. So it's m. So we prove that this c to d mod n is actually m. So that's why once we select m, n, and once we select key e, and once we select another key d, then the encryption and decryption can be calculated very easily. So okay, we now summarize these discussions that in the previous slide as this. So we proved that c to the d modular n is finally equals n. So that means in one encryption side, encryption side, we just calculate the m to the e mod n, we get the c. And then we can calculate c to the d mod n, and we will get back to m. So this encryption and decryption, they basically perform the same operation but with different keys. Then we will actually just analyze this and show that the RSA actually works. Now the next one is we're going to first actually provide some examples, and then we also need to discuss the fundamental questions, whether this RSA secure, right? Because if its RSA is not secure, even though it's correct, it doesn't help us. Okay. Now, before we do any of the examples, let's first actually ask a question. How can we find a multiplicative inverse of a number a modulo n? Is it easy to find it? Now the answer is it's relatively easy to find a multiplicative inverse modulo n. So in another word, if you are given an integer a and n, it's relatively easy to find a b such that the a times b mod n is 1. Okay, I'm going to leave that questions to you for this moment. And hopefully I'm going to actually put this question on the discuss forum, so you can actually, if you can, provide the answers for this. Or you can search for the answer, how to find the multiplicative inverse b of a modulo n. There's an extra algorithm, but it's out there, so let's actually do and find it. So I'm not going to discuss this in here. Now here is a very simple example. Now to generate the RSA algorithm, we need to find n, right? And then to find n, we first need to generate the two prime number p and a q. Let's do it. Now suppose I find the two prime numbers. P is 17, Q is 11. Of course, both are prime numbers. And we compute n by multiply P and Q. So it's a 17 times 11. I got a 187. So I can easily calculate the Euler's totals of n, which is the P minus 1 times Q minus 1. The P is 17, so P minus 1 is 16. Q is 11, so Q minus 1 is 10. So 160. That's the phi of 182. Honestly, if you try to calculate a phi of 182 by definition, it will take a longer time, right? So we have to test each of the numbers, whether the number is relative prime to 187. We need to test the numbers from 1, 2, 3, 4, all the way to 186. And then we're going to select E such that the GCD of E and the 160 is 1. And we actually find E. So you can verify so that actually GCD of 7 and the 160 is 1. It is 1 because E is actually a prime number. So prime number is relatively prime to any numbers, right? And then we find a D. So that the E times D equals 1 modulo 160. So that means, in another word, we find E is 7. We find the 7 times D such that 7 times D mod 160. Phi of n is 1. So we actually find that D is 23. Okay, you can verify this. 7 times 23 mod 160, whether it's 1. It is true. Okay. So we can create a public key PU it's not a KU. It's 7 and 187. And the PR, the private key, is 23,187. So in this example, we find n, which is 187, which is a multiplication of two prime numbers, 17 and 11. And then we find one of the key, which is 7, 187. Okay, we can make this a public key. And then we find a private key, which is 23, 187. We know and the 7 and the 23 are basically create the same kind of pair, right? How can we do the encryption, decryption? And actually, that's the easy part, because the difficult part has been done. Okay, so let's assume we have a plain text. Okay, 88. Now make sure when you select a plain text, make sure the plain text is always smaller than n, which is 187. Okay, so now if the plain text is 88, and then we're going to calculate the ciphertext. So it's 88 to the 7. Remember, that's the first number E, right? 88 to the 7 mod 187. Now we can actually do the calculation, and then we got 11. If you try to calculate by hand, it takes some time, but if we write the computer program, it should be easier. You know, we can reduce the power and also reduce the base, right? We tested this. So we got a ciphertext 11. So we can transmit the 11 to the destination. Now, once the receiving side received the ciphertext 11, how could the receiving side recover these plain text? So the receiving side should have the other key. Okay. So when the sender actually send using the public key of the receiving side. Okay, so that's 7. And then the receiving side should have its own private key, which is 23. And the second part is known, right? 187 is known by both parties. So, but 23 is the key, the secret number. That makes this a private key. So when the receiving side receives the ciphertext, so hopefully only the receiving side knows the private key. So you can actually try to recover the ciphertext. So by doing this math, 11 to the 23 mod 187. That's another huge operation if we try to do this by hand. But by computer, it's really relatively easy. So then you will find out this is 88. Okay, so we can easily just do this. Okay, now let's actually pick another number, say like 141. Say the plain text is 141. Let's do this. Now we're going to actually do the calculation. 141 to the 7 mod 187. And what is this? Again, I can leave that question to you. And then once you got this ciphertext, and then you can verify this by this number, you know, to the 23 mod 180, you will be guaranteed that this is going to be 141. So whatever the number you got to the 23 mod 187, this is going to give you 141. Okay. Okay, let's take a look at a more realistic example. Suppose the sender wants to send a message, say, "How are you?" Now, what the sender going to do? So the sender first going to actually encode these messages into using ASCII code, right? So the ASCII code for H, capital H, is 33. The ASCII code for O, lowercase o, is 14. So we can, for each number, we can convert into the ASCII code, including the space. The space is 62, and here's another 62. These are two space, okay? And the question mark is 66. So we got each of the number. So now let's pick the value n and the two keys. Okay. Now the number n we pick is 11,023. Now, which is actually the multiplication of two prime number 73 and 151. So that's the p, that's the q. Now we p times q get this number. So that number is definitely bigger than any of these numbers. So basically, so that number is actually 5 digits. So it's bigger than any of the combination of these numbers. So we can basically combine these two numbers, combine these two, and combine these two, and combine these two. So then we can actually split this whole message into a couple of blocks. The first block is 3314, which contains two characters, H and O, right? Capital H and O. The second one is 2062. Third one is 0017. Fourth one is 1462, 2414, 2066. So basically, the whole message is going to be split into 6 blocks. And then each block is smaller than the value n, because n is 5 digits and each number is just 4 digits. So they're all smaller than n. So then we do the encryption for p. So let's say for the n, we find the first key E. E is the private key or the public key, okay? So 11110323, that's the public key. Actually, this is actually the very important part of the key is the first number. The second number, n, is known for both sender and receiver, right? And then what is D? We calculate D as this. So E, so D is 5891110023. That's a private key. Okay, that's public key. So we're going to do the encryption. So the first, plain text number P1 is encrypted, 3314 to the 11, because 11 is the key, right? Mod n, so we got this one. So that's the cipher text, we call it C1. And then the second P2 to the 11, mod n, we got this C2. So we got C1, C2 all the way to C6. Okay. Now on the receiving side, so we basically transmit the number C1, C2, C3, C4, C5, and the C6. These are the number we're going to transmit to the receiving side. So once the receiving side received each of the number C1, and then to decode it, the receiving side need to do this math. It's the first one is 10260. So 10260 to the 5891. Remember, 5891 is the private key. That's a huge operation, right? You're talking about the power, 10,260 to the 5,891. That's a lot of calculation. But if you have a computer program, it's relatively easy to do so. And then we will find out after modulo n, you're going to restore back to P1. So same thing with this, it's P2. So that's more realistic question. Now here, let's actually summarize these two examples. So first we need to find the two prime numbers and then multiply these two prime numbers, we got n. And then with the n, we calculate the Euler's totient function of n. So, and then we generate the two keys, E and D. So E and D are multiplicative inverse to each other, modular phi of n. Okay, now the question is, if you actually publish this as a public key, 11 and 11,023. Now the question you may ask, well, if someone got this 11,023, I can easily factor this number, right? Because I can use the math function to factor this number, and I can get these two prime numbers. What are these two prime numbers? 73 and 151. And once I got these two prime number, so I can generate the n. Okay, of course, I already know the n. So if I already factor the n, so I got 73 and 151. So I can easily calculate the phi of n, the Euler's totient function of n. And then I can easily, based on the public key, I can easily find out the other number, 5891. So what's the point of doing this? So this concern is legitimate. Honestly, the two examples that we showed you are not safe. Why it's not safe? Because these two numbers are too small. Whether it's the first number, 187, which is the multiplication of 17 and 23, or even the second number, which is much bigger, but it's not big enough, because that number n is only 5 digits. So it's still small. So we can use a traditional way to factor the number. That's the reason why we want to talk about RSA with extremely big number. So we are talking about a number which contains, 1024 bits for the binary. Or if we convert it into decimal, like this case, then the n should be around 309 decimal digits. So it's a very, very big number, the n. So in that case, if I give you the number n, which contains more than 300 bits, more than 300 decimal digits. Now, can you try to factor the number? Now it's back to the original question we just mentioned, that if we try to factor the number which contains 309 decimal digits, still remember the question? Remember the examples we did? How long it's going to take to factor the number? I forgot the actual number, but it's more than like a billion years, right? So it's technically infeasible, computationally infeasible to factor the number. So that's the reason why we need to select a number which is actually up to 309 decimal digits. Now this number, n, 11,023, that's too small. So you can still use the traditional way to factor it. But with the more than 300 digits, decimal digits, the traditional way is going to take more than a billion years to factor it. So it's computationally infeasible. But still, when you know how this number is constructed, we know the two prime numbers that constructed that number, so you can calculate the Euler's totient function of this number, and then we can follow that procedure. Then we can easily do one way, but not the other way. Okay, so that's something we're going to discuss in part 3. So we're going to choose extremely big number to make the factoring of the number impossible. Or not impossible, but computationally infeasible. Okay, that's the term we're going to use. Okay, I think that's pretty much all for part B. Thank you.